sequences and sums. We already said that if I have AK equal with K, that implies the sequence AK, I can write it like this as a sequence is 1, 2, 3, so on and so forth. And the sum of AK, that's called the partial sum. So we can say Sn is from K equal 1 to n of AK. That will be sum from K equal 1 to n of K. We already did this. It's n times n plus 1 divided by 2. Last time we did this in two ways. We show you this trick with looking at the sum in order and then in the opposite order, summing up the terms, we got n plus 1 divided by 2 in there. So that's one. Based on this, I can do any arithmetic sequence because I know this formula, right? Say now any arithmetic sequence any AK that's arithmetic must be m times k plus n, right? Where m and n are constants. So then I have the sum of the partial sum of the first n terms of that sequence. I can do it very directly if I know the generator, the formula. Sometimes I'm given a sequence that I believe it's arithmetic, but I don't have its controllers, m and n. That are the ones that are actually the generating function. If I want to do this, well, that's just sum of m k plus n, right? Which is n times the sum from k equal 1 to n of k plus n. So now I know this formula of indices on k. That will be m times, oh, I have multiple n's in here. Sorry about that. Let's change those. Let's call them p and q. Is that good? P and q. M times, now I have n times n plus 1 by 2. P times that plus q. So any arithmetic sum, because I can sum the indices, I can easily do any arithmetic sum that way. Now, if I have AK equal k squared, then I have the quadratic progression. 1 square, 2 square, 3 square, so on and so forth. The sum of that progression is sum from k equal 1 to n of AK, which is sum of k equal 1 to n of k squared, which is
for the arithmetic should be p times n times n plus 1 over 2 plus n.
NQ. I'm missing an n here.
Yeah.
Why is that?
Because you're summing like this.
Because I'm summing how many cubes? There's n cubes in there, right? Everybody has a plus q. So if I sum n terms, I get a plus q n times, right? Hands up who's with me, or why this q? Good. So how about this formula? Do we know this formula? I sum up not the linear indices, but the quadratic indices. What do I get? Is there a formula for that? We didn't do it yet, but do we have a formula? N times n plus 1 times 2n plus 1 by 6. You would have to know this to be fluent. I'm not sure we require you to know them by heart, but certainly it could be easy in an exam or a quiz to have these formulas ready, because any arithmetic or quadratic progression can be immediately summed if you know the sum of indices or the square indices. Huh, so how did I come up with that? Well, I knew it from before, right? I didn't do it right now. But we would like to make a proof that that's true in general. So let's see, we're going to make an induction proof here. our statement here, so we're proving the statement of n that says Sn, which is the sum of k equal 1 to n of k squared, that's not needed to prove. This is a definition. We don't need to prove this, but this we need to prove. This is n times n plus 1 times 2n plus 1 by 6. Now that's our statement. That's what we want to prove. The reason I'm stating it like this as a statement is because I want to make an induction proof, and I want to recap how induction proofs work. Induction proofs work like essentially going from the statement of n, proving the statement for n plus 1. This is the induction step. When we do this, we have to state exactly what that means. Many people, students like you, forget about that step because it's already written here. Why write it again? You have to write the induction step before you prove. So in our case, what is this implication from n goes to n plus 1? How does that look like? That is, if sum of k equal 1 from to n of k squared is n times n plus 1 times 2n plus 1 divided by 6, that is the statement n, implies, this implies, how the statement looks for n plus 1. The same property, but not written for n, written from n plus 1. How does that look like? Anybody can tell me that? I want to write this property, this statement, not for n, but for n plus 1. Yes?
It's the sum from k equals n, 1 to n plus 1 of n plus 1 times n plus 2.
Well, if you put sum, you don't need to enumerate the terms.
Okay.
Either enumerate the terms or write it as a
Sorry,
concise
sum
sum.
is equal to.
Equal with what?
Is equal to n plus 1 times n plus 2 times 2n plus 3 all over 6.
So this term is, this part, the left part, is the same form, except it goes, instead of going up to n, it goes up to n plus 1 now, because I'm writing the statement to n plus 1. It's still the sum of squares, but not to n, it's to n plus 1. How did he get n plus 1? Where is n plus 1 from? He replaced this n with n plus 1. How did he get n plus 2? Replace n plus 1 with n plus 1 plus 1, that's n plus 2. And instead of 2n plus 1, how 2n plus 1 became 2n plus 3? Because I put instead of n plus 1, that's 2 times n plus 1, that's 2n plus 2 plus 1, that's 2n plus 3. I would appreciate if you write it here this way. That's correct. But it would be better for you to write it as n plus 1 plus 1, clearly replace n with n plus 1. Times, in here, how do I write that? 2 times n plus 1 plus 1. That makes it more clear where this formula is coming from. It's coming by replacing every n with n plus 1, right? Of course, it's the same formula like before. There's no difference here. I can even write like that, n plus 1, right? N plus 2, 2n plus 3, divided by 6. So now, we didn't prove anything yet. We just stated the induction step. What induction step wants us to do is to go from n to n plus 1. That's what we need to prove here. In induction, if you prove this in general, we have a sequence of implication that statements 1 implies statement 2, implies statement 3, all of them, that every implication is an instantiation of this for different n's. From 1 to 2, I get it from 1 to 2. From 2 to 3, I put n equal 2. I get from 2 to 3, and so on and so forth. So I prove all of them, assuming I can prove the first one manually, or the first two manually, how many I need. Those would be my base cases. My general practice is to leave base cases for the end. That's in contrast with how everybody learns induction. Most people who learn induction do the base cases first. The book does it first. Tutorial online does it first. The regular sections doesn't work. Nothing wrong with doing the base cases first, but I found it easier to do base cases last, because after I do the induction steps, I actually can tell what base cases I need. It's very hard to guess in the beginning sometimes for some tricky problems. What are my base cases? Do I need n equal 1? Do I need n equal 2? Do I need n equal 3, 6? What are the base cases? In here, we can guess what base case we need, right? This is a very simple weak implication. So what would be my base case to make this work? I need n equal 1, right, as a base case. But in some problems, I'll show you later, not that easy to tell what base case are needed. So you do the base cases in the beginning, then you do the proof and say, whoops, I need another base case. I prefer to do them at the end when I actually can tell what base cases I need. But doing the beginning is fine too. So how do we prove the induction step? What's the main idea for this kind of proofs, which are calculations or sum or products and things like that? Main core idea in English, what is it? So, of course, the implication means we can take this as true, right? That's given to me. That's now a premise. So this is induction premise. And this is induction conclusion. So I can use this fact. But what's the main idea? How do I use this in all these induction proofs that are calculation-based? Let's write it here. Core idea. We need to relate some quantity, typically the left side quantity from here, with the left side quantity from here. That's the core idea in induction calculation. How does my new sum relate to the previous sum? Relate the new sum to be computed. What's the new sum? Is this one, right? Sum from k equal 1 to n plus 1 of k squared. That's the new sum. To the old sum, or previous sum. I should say previous. What's the previous sum? Is this guy. Now this is in English. You should always try to do this when you face an induction proof. Is how can I use this to prove that? Typically, you have to discover some sort of relation between what you have to prove, this sum, and what you know, which is the previous step sum. What is, in this case, that relationship? Because that relationship is the key to make this proof easy. Yes?
The difference between the two sums should be n plus 1 squared.
Right, so he's saying this sum is nothing but the old sum plus one more term. That is the core idea of a proof. Of course, there's calculations that you can get right or wrong, but the core idea in induction proof is to relate what you have to do with what you have already. So how do we do that? Well, the sum from k equal 1 to n plus 1 of k squared, we're going to say that's just the previous sum, right? Plus, what's the new term that I'm adding? n plus 1 squared. Right? That's the term that I'm adding to make the new sum. And now, how do I use the induction premise? Of course, I'm going to replace this sum, which is appears here, with the formula that I already have, because premise means I already know that. So then I'm going to say that's n times n plus 1 plus 2n plus 1 divided by 6. I took this from here. Plus my new term, n plus 1 squared. How many people with me? This is the hard part in induction. Figuring out how the new stuff, or the n plus 1 stuff, depends on the old stuff. From here on, it's just calculation. Of course, most people get it wrong. I do too all the time. But that's just grinding calculations. You got to be careful a little bit with that. And in particular, it's nice in induction proofs that you know where you have to end up, right? So if I just tell you calculate this, if you make a mistake, You may not know you made a mistake. But in induction proofs, you know you have to end up in here. So it's pretty easy to tell you made a mistake because the stuff that you have, it's not this stuff that you have to be at, right? So we're gonna try to get to this point. How do we get from here to here? We have this, and we want to show that this is effectively this guy right here, right? I can see an n plus 1 common factor, and that's common factor here, right? So I can just put an n plus 1 in front of it, right? Let's write it by 6. I get a 6 out too. So what's left from this guy if I took the n plus 1 out? N by 6. What's left? N times 2n plus 1. And now what's left of this if I took the n plus 1 out? It's 6 times n plus 1, right? Because the n plus 1, it's 1 left. I took, there's 2 n plus 1s here. Orange times an orange. I have an orange in front of the parentheses, so the other orange remains inside. And there is a 6 that I divide by 6. I have to multiply by 6 to make it right. So now, I've seen the n plus 1 already. I'm looking at it. Induction proofs, I'm always with one eye on what I have and with the other eye on what I'm supposed to go. Because that's the only way to match those things, you know, easily. So I have the n plus 1 by 6 right here. What do I need to do? I need to get n plus 2 times 2n plus 3, right? So how do I make this to be n plus 2 times 2n plus 3? N plus 1 by 6, obviously that will stay there, not gonna move. Now, what is this? 2n squared plus n, right? Plus 6n plus 6. So, n plus 1 by 6. This is 2n squared plus, I need to regroup those terms. N, one apple plus 6 apples, that is 7 apples. Now, how do I group 7 apples to get this? How many and how many? I think I need like 2n squared plus 4n plus 3n plus 6. Because if I put the 7 apples as 4 plus 3, I'm going to get now n times 3 is 3 apples, and 2 times 2n is the other 4 apples. So that you can, this is n plus 1 by 6 times 2n n plus 2 times 2n plus 2. Okay? So I've done my induction step proof. Again, key to this proof is to say, how do I relate the new stuff to the old stuff? The rest is just calculations. And I don't have a base case. But what I did prove, I would like to write this down as the way we did it before. Here's what I proved. I proved the statement of 1 implies statement of 2 implies I just prove all of those, right? Because every one of my induction steps in there, I prove it for a general n. That's what I prove. It's actually one of these implications. I don't have to do those separately. I just did them, all of them at once in a general case. From any n, I can go to n plus 1. That is, from 5, I go to 6. From 7, I go to 8. From 11, I get to 12, so on and so forth. So I've got this done. That's the induction, effectively the induction step proof. Now I need a base case, so I'm looking at my implications. I say, which one should I prove true to make sure everything is true, right? I mean, this doesn't guarantee that all the statements are true. When can I get this implication proven, but they are actually all false? Is that possible? Is it possible to have this induction step proof, which means that, but all of them to be false? I mean, why do I need a base case?
All those are true only if the original statement, like statement of 10, is true.
Right. So it's possible that this checks out, the induction hypothesis versus conclusion works out as an implication, yet none of them is true because false implies false, right? So I need to prove the first one true to make it all work. But in order to determine which one I need to be true, it's better to look at it like that in a sequence and say, if I prove this one true, then everything has to be true from here. So my base case will be n equal 1, which in this case is what? This is manual. Base cases are manual. We don't do any sophisticated stuff. So in here I get 1 square has to be 1, what is it? N times n plus 1, 1 times 3 times 3 by 6. Is that right? So if I plug in here 1 times 2 times 3 divided by 6. Is that true or false? Marker check. I don't have to explain why that's true. It's a simple arithmetic calculation. In here I only need that base case. All right? So we have this formula that's good for quadratic sequences. Like before, I could take any quadratic sequence now. Quadratic sequence. So the generator of a quadratic sequence is AK is say P times K squared plus Q times plus say R. When P, Q, R are the controllers constants or the generators. In any problem with sequences, arithmetic, quadratic, geometric, of any kind, any sort of pattern, your biggest job is to put your hands on the controllers. Once you have P, Q, and R, or in here P, Q, or whatever is the controllers, you can do so many manipulations with them. The hard part of sequence is if you don't know P, Q, and R. But once you have them, any calculation becomes very, very easy. So in here, how do I sum up the partial sum? Sn is the sum from k equal 1 to n of ak. Well, that's just the sum from pk squared plus qk plus r, right? So I break this into 3 sums. It will be p times the sum of k squared plus q times the sum of k plus how many r's are here? N r's, right? Because I have r, n times. So now I replace the formulas in this. I have this and I have this as a formula. So I say, okay, that's p times, the formula is just the one we've done here. It's n times n plus 1 times 2n plus 1 by 6 plus this formula we did before, n times n plus 1 by 2 plus ni. So I can sum up pretty quickly a quadratic sequence if I know it's generating PQR or ABC coefficients, sometimes it's called. That's true for any quadratic formula. Once I put my hands on the coefficients, I can just apply these formulas. You don't have to prove this or this. We did it in class, it's in the textbook, so you can just, you have to remember the formula. Sum of the squares is n times n plus 1 times n plus 1 by 6. So once you know that, boom. How about geometric stuff? Geometric sequence has the form AK is P to the K times Q or something like that. Sometimes maybe P to the K minus 1 times Q. Like if you want to start with K equals 0, but that's a small variation. And we have a formula for this. The formula that we need, of course, if I'm to sum up this from k equal 1 to n, I get sum from k equal 1 to n of p to the k times q. Q is a common factor to everybody. P to the k from k equal 1 to n. So I want to write this in so you guys can see it. It's p plus p squared plus p third plus p fourth plus p to the n. That's what this formula from with exponents k equal 1 to n. So we done this last time. We have a formula for this that we proved already by induction last time. I don't want to prove it again, but I'm going to state it right here. P plus p squared. The formula includes a 1 here. So it starts at p to the 0. Anybody remembers the formula? So be careful with this. This formula that I'm giving you starts with a 1, and many problems don't have the 1. Many problems when you do a sequence start with p to the 1 instead of p to the 0. So all you have to do is subtract this 1, but be careful with that, not forget to subtract the 1. So what is the formula? Yes.
R to the n minus 1 over.
What is it?
R to the n minus
P.
P to
in
the
here.
n minus 1 over.
If we said if p is not 1, because I can't divide with 0. So what happens if p is 1? If p is 1, I can sum it up manually, right? 1 plus 1 plus 1 plus 1 plus 1. How many 1s are here? Starting at 0, ending at n. N plus 1. So I have to sum it up manually. If you don't see anything, right? You're just listening. Nice. All right. Okay. So since I have this formula, I can apply it right here. So how do I say Q is Q? How much is this stuff? Let's assume in here I'm going to put that P is not 1, because I don't want to complicate myself with the other case. So I'm in this case. Can I say P at n plus 1 minus 1 divided by P minus 1? Would that be correct? I replace Q is Q, and I replace this sum P squared P with this formula.
You need to subtract the 1.
This formula includes the P to the 0, but my sequence does not have P to the 0. So this would be including the P to the 0. So what do I have to do? Subtract 1. And where is the 1 going? Is it Q times 1 or is outside the Q? This minus 1 that comes from I added the P to the 0, is that in a times Q or not times Q? Okay. So this is P to the 0 that needs to be taken out, because if I have, some problems will have P to the 0 and you have to include it. Some problems will not have P to the 0, and if you apply this formula, you have to take out the P to the 0, the 1. Yes? Where is that? Here?
No, like instead of minus 1, you subtract the bottom.
The main formula?
No, below.
Here?
Yeah.
Why is it n plus 1?
No, why can't you subtract that?
That's it, only if P is 1.
Okay.
This n plus 1 is 1 plus 1 plus 1 plus 1, n plus 1 times. But it's only if P is 1. If P is not 1, it's this formula. So now I'm assuming here P is not 1, because to apply this formula, I can't do it when P is 1. P is 1, that means divide by 0. It doesn't work. Okay, so I can sum up this way geometric series, because I can always bring a geometric series to a sum like this with some coefficients like Q on the side, and then apply the formula and get the answer. One thing that is going to happen, if you do it, this may be hard to compute in decimal. If this is a 2 or 3 to some power, it's not easy to compute this. If, say n is a sum up from 0 to 100, and then you get 2 to the 101, you can't put that in decimal, so you have to leave it as 2 to the power 101 on your paper, because it's not computable in decimal value. The other thing that's very important here with this formula is the limit, the infinite geometric series. So the one that doesn't go to n, it goes to everywhere to infinity, right? So that looks like what? P to the 0 plus P to the 1 plus P to the 2 plus P to the 3 plus P to the 100 plus, it goes on and on and on and on. What is this? How can somebody keep going on and on and on and on and have an answer to it? What kind of answer I'm looking for here?
If P is between 0 and 1.
Okay, so clearly we have to distinguish two cases, right? Let's say, actually I want to distinguish three cases. When P is 1, when P is bigger than 1, and when P is, you say, between 0 and 1. So I have three cases here. Right, so the case you want to say is this one, right?
Yes.
Right.
Then
How do I think about this geometric infinity? So this infinity, what does it even mean? Like what mathematically, I mean on the board I say dot, dot, dot. But mathematically, what do I mean by it? Because dot, dot, dot has to mean something. When I say a sequence, dot, 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 that means all the terms of that sequence. It's like an infinite sequence. In here, what do I mean?
And this is the limit of the,
Very good.
yeah.
That's the limit when n goes to infinity of p to the 0 plus p to the 1 plus all the way to p to the n, right? I'm summing up a finite geometric sequence up to the n, but then I'm taking that value to infinity. What's the limit of it? So I think it's easy to see if p is equal to 1, what's the limit? 1 plus 1 plus 1 plus 1 plus 1 plus 1, infinite amount of times. What's the limit of that? There is a limit, but it's not a number. What is it? Infinity, right? How do I write infinity? It's an 8, like down like that, right? Infinity is not a number, but it is a limit. Things can go to infinity in the limit. So everybody can see that if p is equal to 1, I get 1 plus 1 plus 1 plus 1 plus 1, infinite amount of times. That's infinite. What happens if p is bigger than 1? Obviously, it's going to be infinity because it's going to be bigger than this guy, right? And what happens when p is smaller than 1? Then my limit becomes, I can apply the formula, limit from n goes to infinity of this formula, p of n plus 1 minus 1, p minus 1. I can apply the formula because I know for sure p is not 1 in here. It's between 0 and 1. So what's the limit? How do I compute the limit of a monster like this when n plus 1 only affects 1/3 here? So p minus 1 is not affected by the limit. Minus 1 is not affected by the limit. So I could say this is remains p minus 1, this remains minus 1. The limit only applies to this guy because it's p at n plus 1, right? So this is limit when n goes to infinity of p at n plus 1. The rest doesn't have nothing to do with n, therefore the limit doesn't change. It's fine. So now what's that limit? Why is it 0? So why is this limit 0? P is a number between 0 and 1. For thinking purposes, let's say it's 1/2 or 1/3. Why is 1/2 when I raise it at a big exponent, bigger and bigger and bigger, I go all the way to infinity, becomes 0? Somebody else, yes?
Because the denominator gets bigger, so basically like it's getting bigger.
It's 1/2. If I raise at the power like 1,000, I'm getting 1/2 to the 1,000. The 1 remains a constant. 2 to the 1,000 becomes a very big number, arbitrarily big number. Therefore, the fraction becomes arbitrarily small. So that's if it's 1/2, but it works with any p. Like what if it's not 1/2? What if it's 0.9562? Does it work? When I multiply a p with itself and with itself and with itself, and that value is below 1, I keep decreasing at a steady rate, I have to hit the floor that's 0. That's not a mathematical argument, and you are able to make a mathematical argument, prove that the limit, because we give the limit definition, prove that the limit of this thing is 0. It's not hard to do. If that's 0, it's minus 1 divided by p minus 1. So now if I reverse the signs, I get 1 over 1 minus p, right? So, did I tell you I'm writing homework 6? I did. The weighting. There's a problem with this in there. But the 2 hard problems were deleted. So, it's only the easy ones that are in. Sorry about that. I did my best. The hard ones, I don't know, got lost. Yeah, we'll make them available, the hard ones too. But anyway, it's not that easy. I mean, it's not like trivially easy. It's just not so hard. So there's something with this 1 over 1 minus p in there. Okay, so now we have the basic sequences that we need. We can make all kinds of arbitrary induction proofs. Let's make 2 or 3 of them. Actually, let me state something, one more thing about, as an exercise here. So exercise. What if I tell you there is a quadratic progression that looks like 12, 20, 30? But I tell you it's quadratic. How do you find the coefficients? So the coefficients are the ones that are p k squared plus q k plus r. Or in some problems, if you want ak squared plus bk plus c. How do you find the coefficients p, q, r, or abc? If you know it's quadratic. Yes?
Your system of equations.
Replace, get those numbers for, this has to be k equal 1, 2, and 3, right? So if it's quadratic for sure, like somebody tells me it's quadratic, I'm going to say, okay, well, put k equal 1, what do I get? P plus q plus r must be, sorry, let me make it clear, p times 1 squared plus q times 1 plus r, that has to be 12. If I put k equal 2, I get p times what? 2 squared plus q times 2 plus r has to be 20. And then if I put k equal 3, I get p times 3 squared plus q times 3 plus r has to be 30. So the very important thing is that even though the sequence is quadratic, these equations are linear. In unknowns p, q, r. Right? The actual system that I've got here to solve for p, q, r is not quadratic equations, that's just linear equations, which are what? P plus q plus r is 12, 4p plus 2q plus r is 20, and 9p plus 3q plus r is 30. So what is the answer if I solve this system? Somebody maybe can solve it. What do I get? P equal, Q equal. Here's what I've got here. And R equal. Is that true? Does it work? 9p plus 3q, if p is 1, this is 9, 3q is 15, 15 plus 9, 24 plus 6 is 4. Now, I didn't tell you how to solve it. Do you know how to solve a system of 3 equations with 3 unknowns? You take one variable from one equation as a function of the other, replace it in the other 2. How many people would know how to solve such a system? That's good because it might be in the quiz next week. Okay. So we need to be able to solve a system of linear equations. Those systems are easy. They can get complicated if the equations are not linear. If you get p squared or square root of p or p cubed in there, that's a hard system.
Do we need to write our work on the quiz for like solving system equations?
Say louder.
Do we need to write our work for like show our work for solving system of linear equations?
Yeah. You would have to take, I don't know, q from here, say q, if I take out q, q will be who? 12, minus P minus R, replace into the other ones. Yeah. I'm not promising you a system of equation will be in the quiz. I'm just saying it might be, and you have to be able to solve it.
We'll have to use like matrices in our calculators to solve those and show that work.
Yeah, if we allow calculators. Okay. So I'm not going to insist on that, but this is something that if you don't know, you should come to office hours, to me and say, hey, I don't know what you said in class about those systems. I have no clue what they are. Can you show me how to solve them? And we'll do that at office hours. Okay, so that's a way to do this for quadratic and linear equations if you know they're quadratic or linear. But for some other ones that you don't know, just have to trial and error. So let's do another proof here, something else with sequences. Here's how about I have this Sn is 1 cube plus 2 cube plus 3 cube plus n cube. And I have a formula for it. If I don't give you the formula, there's two problems. Problem one, find the formula. And problem two, proof. Typically by induction. You don't have to do it by induction. You know, I showed you a Gaussian trick last time that was saying if you sum it up in one way and then the other way and you find the right trick to sum it up, maybe you get the sums right. That is extremely dangerous to try that way. You can spend enormous amounts of time to find the right trick and not get it to work, right? So I think by induction is the most straightforward mechanism that's reliable and it's going to work. The problem with this is that we have to know the formula first. Proofs by induction requires to know what to prove. Because if I don't have the formula, I can't write an induction step in there. Finding those formulas can be quite tricky because it requires a lot of trial and error, right? I could say, okay, if what does this sum looks like? Is it, the first one is 1, then I have 1 plus 8, that's 9. Then I have 1 plus 8 plus 27, what is that? Add to this one, add 37. 36. 36, I need to add 4 cubed, which is 64. So 64 plus 36? Right? I mean, it takes some trial and error to figure out what this formula is. In my opinion, finding the formula is the hard part. It requires creativity, trial and error, and requires you to know some higher level mathematics, which says that if you sum up a bunch of cubes, you are likely to end up with what kind of polynomial there. So if I sum up linear arithmetic formulas, I end up with quadratic. If I sum up quadratic, where is it here? I ended up with degree 3 polynomial, right? Everybody sees that? This is a quadratic sums of quadratic terms, and the result is degree n times 2n. What degree is that? Cubed, right? So if I sum up cubes, what should I get? Degree 4 polynomial, looks like. But again, to know why this is true requires higher level algebra, right? You can think of the differentials a little bit. When you differentiate a polynomial of degree 4, what do you get? A polynomial of degree 3, and the differential is effectively deltas between the sums, right? So I think you can think about it that way. The hard part is to come up, this is probably polynomial of degree 4, so I could make it work by saying, okay, there must be some n a to the 4 plus b n cubed plus c n squared plus dn plus e, right? Maybe. And now find a, b, c, d, and e by plugging in different terms. This requires creativity. In most problems will be given to you, but when it's not, this is not a simple thing to figure out what the form is with no clue at all, no indication. So I'm going to put the formula right here. And then we make a proof. 1/4 n squared times n plus 1 squared. No surprise, it's a degree 4 polynomial. So how do we make a proof? First of all, we do the induction step. Induction step, we have to state it first. Remember that. Here's the induction step, Sn. I'm going to call Sn sum from k equal 1 to n of k cubed, right? That's what it is. Concise form is sum of the cubes from 1 to n. So I'm going to say if the sum of k equal 1 to n of k cubed is 1/4 n squared n plus 1 squared, then that's the induction implication. What's the formula for n plus 1? How do I write the whole thing? So again, what am I doing here? I'm doing a statement of n implies a statement of n plus 1. That's my induction step. So what's the statement for n plus 1? The same exact statement, just not for n plus 1. Somebody else? Yes?
It would be the sum of k to the third from k equals 1 to n plus 1.
Of same k cubed, right?
Yeah, k cubed. Yeah, is equal to 1/4 times n plus 1 squared times n plus 2 squared. Yeah.
Right? That's saying, if I would know it true for n, it will also be true for n plus 1. That's back to these statements, right? I just wrote there all these statements together because I wrote it for a general n. For n equal 2, I'm from 2 to 3. From n equal 3 is from 3 to 4. From n equal 4 is from 4 to 5. So I wrote down all these implications. My meaning here, in logical sense, it's for any n starting at 1. Right? I'm saying this is true for n equal 1, for n equal 2, for n equal 3, all these induction steps. So how induction works again? It's a series of implications from 1 to infinity, not necessarily from 1. Some inductions start from n equal 3 or 4, whatever. But it starts from somewhere and it goes all the way to the end. And typically it's an implication one by one, which we don't prove separately. We prove it as a one step from any n to n plus 1, which means we proved all of them in one shot. And then of course we're gonna need a base case to start somewhere. Something has to be true to make all of them true. So how do we prove this? Core idea, like before, in all these calculations, we have to look at the new guy and say, who's this? This has to be related somehow with the old guy, because that's my handle, right? To make use of the premise, I'm going to have to look at this. This is what I have to calculate here. How do I relate this with what I already have? So core idea is to relate the sum from n equal 1 to, sorry, k equal 1 to n plus 1 from k cubed to the old one, k equal 1 to n of k cubed. That's very easy. So how do we do that? This sum of cubes up to n plus 1 is simply just the previous sum. But because it's all the cubes plus 1. What's the next cube? That's not in the previous sum, but it's a new sum. Yes?
N plus 1.
N plus 1. So now how do I use my premise? I already have a formula for this sum, right? The premise is telling me what this sum is. I have it right here. So I'm going to say, okay, I know what that is. That's 1/4 n squared times n plus 1 squared, to which I'm adding my n plus 1 cube. So this is this term, right? This is the premise. I just replace this sum with that. And now again, I have one eye on what I have and one eye on where I'm supposed to go. So here I am, that's what I have. And where am I supposed to go? I want to get this, right? This is like somebody correctly pointed out n plus 2 squared. N plus 1 plus 1 is n plus 2. So what do I see? What's easy to get? I want to get this 1/4 n plus 1 squared out of it. To get rid of, I mean, not to get rid of, but to be done with that part. So I would like to write this as 1/4 n plus 1 squared in front times something. Because if I do that, I already have 1/4 times n plus 1 squared. I only need to worry about this part. Hands up who's with me. So how do I do that? I force this common factor, whether it's there or not, I force it out. From the first one, 1/4 n plus 1 squared, that looks pretty good, right? What's left of it?
N squared and 4n plus 1.
What about this one? I got there's 3 oranges multiplied together here. N plus 1 is an orange, so there's 3 of them. So I got 2 of them in the front, therefore how many I have inside?
1.
I have 1, n plus 1 squared, sorry, just 1, because I got 2 out. But I got the 1/4 out, which was not. So I have to put that back, right? So that means 4, that. So now again, I still have one eye to what I have and one eye to where I'm going with this. 1/4 n plus 1 squared is 1/4 n plus 1 squared. That's going to die in there. That's not going to move, right? That's nailed down. It's going to stay. So I only have to worry about the remaining part, n plus 1 squared. Well, this is, let's open the parentheses, n squared plus, how much is that? 4n plus 4. Is that what I need? Is it n plus 2 squared? Good, so I just write it down. 1/4 n plus 1 squared times n plus 2 squared. Done. Now, of course, I picked to do in class the easy ones, right? So keep that in mind when you do your homework, that not everything is so bread and butter. Okay, so I've done now these implications right here, all of them. What do I have to do? If my implications really look like this, not all induction proofs will look like that, by the way. These ones, simple ones, so-called the weak induction, they look like that. And if an induction step looks like this, what do I need for a base case? Somebody else. What do I, if I already proved all those implications with the induction steps, what do I need? Statement of 1. But remember, not all inductions are so easy. So before I move to statement of 1, actually let's do that first. Statement of 1 is base case. So what do I need to do? Just plug in the values and verify that it works. So it's 1 cube equal to, what's my formula? 1/4, 1 square, 1 plus 1 square. Is that true? True or false?
True.
Here's why I'm saying the base cases are not that easy. So in here, I can do base case n equal 1. But here's how it could be that's still an induction problem, but the base case is not so obvious. What if I prove by induction steps? So this I'm going to call weak induction. Here's another way that things could work out with induction, but not so nice. Maybe I have from statement of 1, I get statement of 3. And from statement of 3, I get statement of 5. And from here, I get statement, all the odd ones, 99, and keep going. And separately, also with induction steps, maybe I get a statement from 2 implies a statement of 4, implies a statement of 6, implies the statement, whatever statement is whatever I want to prove, of 100. Now this is still, with induction, I prove 2 sets of implications. From 1 I go to 3, from 3 I go to 5, from 5 so on and so forth, and from 2 I go to 4, 4 to 6, so on and so forth. Now what base cases I need to make this work out for me, to be true everywhere?
Statement 1 and 2.
Hmm?
Statement 1 and 2.
I need a base case here, and I need a base case here. Right? Because if I have just one base case, it's going to prove those ones are true, but nothing about this. Right? So that's what I need here. It may be in some problems that the induction step is not. What induction step will be this? Proving from what? How do I write the induction step here? It's from 2k plus 1 going to, or 2n plus 1? 2n plus 3, right? From an odd to the next odd, and in here be from 2n going to. This may be as two different induction steps, or it may be an induction step that has cases in it. If it's odd, I prove the next odd. If it's even, I prove the next even. And this is not the most complicated case. I may have things jumping around all over the place, right? I may have statement of 1 implies statement of 2. But then to prove statement of 3, I need both of them. I may need statement of 1 and statement of 2 implies statement of 3. And then for 4, I need all the previous one. Statement of 1 and statement of 2 and statement of 3 implies statement of 4. So in here, see, every time I wanted the next statement, all I had to use is the previous one. And that worked out. But some proofs, to get to the next step, is not enough to just get the true previous one. You have to get through all the previous ones. This has a name. This is called strong induction. In here, what base cases do I need? If I prove all these implications all the way to the infinity, what base case I need to make everything true in here?
Just 1.
Can I do just one? If you follow, if this is true, then the second one is true. Now both of them are true, so the third one is true. And 3 are true, the next one is true, so on and so forth. I find it easier to always figure out the base case after the induction steps, because I have a schema like this in mind, what implies what. And then I tell everything that has no implications into it, like statement 1 or here statement 1 and 2, those got to be base cases. If it cannot be implied from other things, they have no arrow pointing to them, that means they are base cases. And I may have 2, 3, 4, 6 base cases, depending how the implication structure is working. So we'll see some problems very soon about when the induction is not so smooth and implies 2n plus 1 all the time. Yes?
In your proven base cases, say you end up in a proof that statement 1 is false, would that mean that the whole thing is false, or would it be just undecided since the false can also be true?
Very good question. So suppose we get this, I think what he's saying is we get this implication proved with induction steps, and then we try statement of 1, and that's false. Now what? First of all, it doesn't mean the rest of them are false, right? Because false can imply true. So I could still have a true case. Now if this is false manually, I plug it in values and I get it false, maybe it doesn't start from here. Right? My problem, whatever limit or consequence or property with brothers dating sisters, whatever it is, it may not start from 1. Maybe the property starts being true from 3 or from 5. In fact, that happens a lot on asymptotic functions. You know, this kind of thing that you have to prove a times 3 to the n eventually is bigger than b times 2 to the n. For some starting any n bigger than some starting point. You ever saw this kind of problem where it says this function will beat this function eventually, no matter who A and B is? This is the kind of problem that you're going to hit in algorithms a lot, because those running times of algorithms, they're going to say it's like 3 to the n roughly, or 2 to the n, or maybe n to the 5th, or something like that. And say asymptotically, when n grows very big, this function will dominate. But back to his comment, well, when does it start dominating? What is the point at which this function beats that function? It's going to depend on A and B, right? If A equal B equal 1, this becomes 3 to the n bigger than 2 to the n. It starts from any n bigger than? It works at 0 or not? 1. Right, but what if A is 1 over 100 and B is 100? Then I get 3 to the n divided by 100 has to be bigger than 100 times 2 to the n. That's not going to happen so early, right? How do I solve this? When does it happen? So I need it to happen from n bigger than n0. The question is, where is n0? I know it's going to happen because high-level exponentials will always beat low-base exponentials. That's just a property of mathematics. You take derivative and it's positive, right? But when? That could be the case, like he's saying, it may not work for n equal 1 or 2 or 3 or 4, but at some point it's going to start happening. So I could try to solve this equation. What do I need? 3 by 2 to the n is bigger than 100 times 100 is 10,000. So what is n roughly has to be? When is this going to happen? How do we solve this equation? When is this 10,000? When n is roughly log base 32 of 10,000. That's a value. Of course, I'll have to take the floor of it to make it true. I'm just giving a quick example where things will happen, just I don't know at what starting point, and that the same may happen with induction. I have to figure out if this is false, revise my statement and my problem to say, okay, it's not starting from 1, it's starting from 5. Let's do a few more. Here's another one. 1 squared plus 3 squared plus 5 squared plus 2n minus 1 squared is 4n cubed minus n divided by 3. So if I put an index here, can I say Sn equal to that? Would that be okay? I mean, the problem with these sums that are not containing, in this case, all the squares, it's just the odd ones. You got to make sure you index it properly. Like if you say S2n minus 1, that would be incorrect. Because what's the next S now? If I say that. I mean, I can say that with the condition that the next S is who? S2n plus 1, right? I think it would be easier to not do that, to say this is Sn, and then the next one is going to be who? Xn plus 1. Is that going to work? Who is Sn plus 1? 1 squared plus 3 squared plus 2n minus 1 squared plus what's the next term? Right? So now, if that's my formula, what's my induction step? This is still a weak induction. It's from n implies to n plus 1, right? If Sn is 4, so what is that? Sum of k equal 1 to n of, what is it? 2k minus 1 squared? Is that correct indexing of the sum? So what I said about indexing, when you write it in concise form, you gotta make sure what you write here actually corresponds to the sum. A good way is to check the first term and the last term to say, for k equal 1, what do I get? 1 squared. For k equal n, what do I get? 2n minus 1 squared, and I get all the odds in between. So that's true. So if that is 4n cubed minus n divided by 3, what is this for n plus 1? Sum from k equal 1 to n plus 1 of, is this indexing state the same?
Yes.
Right? That will have to be who? 4 n plus 1 cube minus n plus 1 divided by 3. So how do I prove that? Like always in these calculations, we have to relate the new guy to the old guy. The relation is very easy. Sum of k equal 1 to n plus 1 of 2k minus 1 square is just the previous sum plus what term did I just add? What square got added there? 2n plus 1 square. Not k. K is the index that's done the summation. The next term is the term that comes right after it, 2n plus 1 square. So now I'll use the induction hypothesis to say that's 4 times n plus 1 cubed minus n, 4n cubed minus n divided by 3 plus 2n plus 1 square. Now, this I know because this is that from the premise, and now I have to do something to manipulate this into getting that. The easiest way here, I think, is to first manipulate this one, not this one. I find it easier to say, okay, wait a minute, what is that thing that I'm trying to get to? That is, how do I open those squares? 4n cubed plus 12n squared plus 12n plus 4 minus n minus 1 divided by 3. Because it's n cubed plus 3n squared plus 3n plus 1 times everything times 4, right? So if I manipulate the terms a little bit, I get 4n cubed, 12n squared remains. What happens to these guys? How many n's are here? 11 n's. And then how many free terms? Plus 3 divided by 3. So that's what I'm trying to get. I'm going to need this 1 over 3 in the front to nail that down, 1 over 3. But then what's remaining in there? I get 4n cubed, right? Minus n, that's from the first part. And then what, well here when I open parentheses?
3.
It's 3 times that, but I want to open parentheses in the same time. How much is 2n squared? This is 4n squared plus 4n plus 1. Now I have to multiply with this 3 which I took in front of the parentheses, so that becomes
12n squared plus 12n plus 4 plus 3.
Is that equal to that? The third is 1/3. I have to check inside. 4n squared is 4n squared. 12n squared is 12n squared. Minus n plus 12n is 11n. 3 is 3. So that's done. Of course, I need a base case. This is a simple induction. So the base case would be n equal 1. In that case, I have 1 squared is who? 4 1 cubed minus 1 divided by 3. Is that true? Let's check another one. Just for I don't need it, but I'm just going to verify it. What would be n equal to? 1 squared plus 3 squared is 4 times 2 squared minus 2 divided by 3. Is that true? How much is 4 2 squared minus 2 divided by 3? 4 times 8. 32 minus 2, 30 divided by 3. 10, and this is 1 plus 9, 10. Okay? So I can do a lot of calculations like this. And you're gonna have to do some, of course. Here's another proof. That's not a calculation. Induction proofs not calculating sums. First example I have here. Three divides n cubed plus 2n. For every n bigger than 0. That's a natural number. Okay, so let's try out the induction step. If I do induction by n, of course. So the step is if 3 divides n cubed plus 2n, then what? This is my statement, right? Statement of n is this logical property. That's divisible by 3. So I need to prove all of them being true. So what's the next statement? 3 divides who? n plus 1 cubed plus 2n plus 1, right? That would be the simple weak induction. If n is true for n, is true for n plus 1. So it's not very different than before. We have to relate. How do we do a proof here? Relate the n plus 1, 3 cubed plus 2n plus 1 to n cubed plus 2 to the n. But relate means not in general, just relate divisible by 3. The only relation that we care about is the divisibility by 3. We don't care about magnitude, just how stuff is divisible by 3, what are the reminders by 3, things like that. So how do we do that? n plus 1 cubed plus 2n plus 1 is who? It's n cubed plus 3n squared plus 3n plus 1 plus 2n plus 2, right? So how do I relate it to the previous one? I'm looking at the previous one, n cubed plus 2n, n cubed and 2n. That's the previous one. So it's n cubed plus 2n, that's the previous part, plus the remaining ones have a 3 in common. I could do a 3 common factor, right? It's an n squared plus n plus 1 plus 2 is 3, so it's 3 times 1. So now I know from the induction hypothesis this is a multiple of 3. Right? Because the induction hypothesis tells me 3 divides this guy. So it's a multiple of 3. That's from induction premise. Plus this is also a multiple of 3. Because it's 3 times something. Another multiple of 3. And then of course when I add those things up, I get a multiple of 3. Ends up with me. Okay, very simple, right? Here's another one. Oh, by the way, do I have the base case here? Yeah, so let's do some base cases. Base case is 3 divides 0 cubed plus 0 3 divides 1 cube plus, that's 2 times 0, right? 2 times 1, is that true? I do 2 base cases. This is an important inequality in mathematics, but easy to prove by induction. Bernoulli inequality or approximation. It states if x is bigger than -1 and n is a natural number, implies 1 plus x at n is bigger than 1 plus n times x. Very important inequality. If you do a little plot here, what happens with this inequality, this is x here. When x equals 0, what is this? This is 1, right? And this one here, it's also 1. Both are 1, right? When x equals 0. Now from here, the exponential goes up. That's 1 plus x to the n. But the linear function goes straight. That is 1 plus nx. So you can see how the exponential is always bigger than that. It says when x is bigger than -1, what happens at -1? So let's see what happens at -1 here. At -1, what is this function?
0.
0. Both of them are 0, right? Oh no, this is not 0. How much is this? Right, so this is the exponential, this is the negative n. So this function at x equals 0, x equals -1. At x equals 0, I have 1 equal with 1, and at x equals -1, I have 0, and this one is 1 minus n, so that will be bigger than that. Our point is here not to prove it with calculus, but the main implications are in calculus. We just prove it by induction. So by induction by who? There's 2 variables in here. We can't really use induction by x. X is a real number. So induction requires countability of the steps. We can't do it by x. So induction by n. So what is the step? I need to go from statement of n to statement of n plus 1. So it's 1 plus x at n is bigger than 1 plus nx. Implies, how do I write the same statement for n plus 1? Yes.
1 plus x plus 1 to the n.
At the power n plus 1, right?
Yeah.
Because it's the power n becomes n plus 1, has to be bigger than?
1 plus x times n plus 1.
Now that's what I want to prove. So how do I do that? How do I prove this is true? I need to start in here. And I think the creativity step I have in my paper here is to multiply this on both sides by x plus 1. Which is positive, right? Why is it positive? Because x is bigger than -1. So when I multiply with a positive quantity, what happens to inequality sign? Remains the same, right? So this one becomes 1 plus x at n plus 1, right? is bigger than 1 plus nx times 1 plus x. So now I've got my left hand term, that the one I want here. 1 plus x at n plus 1 is bigger than, I have to open parentheses here, and I have to keep an eye of what I'm trying to get at. So I do 1 plus nx plus x plus nx squared, is that correct? So now I'm looking at my term and I'm saying, how do I get something that's close to, I want to end up in here. So I still have on this side 1 plus x n plus 1. I can write this as 1 plus x times n plus 1 to get that, what I want. And what's left? If I use those three, right? I still have n plus x squared. This is a direct proof, right? I mean, all these statements I know. I've got from the stuff that I know to something I know, something I know. This is not the one thing, wishful thinking, I want that to be true. This is actually going this way, the reasoning. So now, I've got this bigger than this. Can I conclude from here it's bigger than this part, right here? Why is that? Because this thing is a positive value, no matter who x and who n are, right? We all know that. N is a natural number. X squared is a square, therefore positive. So this whole thing in here is positive. Therefore, this is bigger than 1 plus x at n plus 1. That proves the induction step. This is weak induction. So what base cases I need? I need a beginning. 1 plus x at 0 is bigger than 1 plus 0 times x. And let's do, this is n equals 0. I can do n equal 1 too. 1 plus x at 1 bigger than equal than 1 plus 1 times x. Are those things true? How much is this? This is 1, right?
Yeah.
And this is
1.
actually equal. And this is 1 plus x. This is 1 plus x. So the cases where those two functions are equal are for n equals 0 and n equals 1. This is quite useful in a lot of approximations when you have to deal with a nasty exponential function that you don't know how to handle. It may be easier to say that's approximately that. The theorem is a little bit more strong. It's not just an inequality. When x is close to 0, this becomes a very good approximation.
Why have you used 2 base cases for the last 2 problems instead of just 1 base case?
True. I don't need that. That's what you're saying. Yeah. Not needed. Because it's a simple implication sequence, I only need to prove the first one. But I like to do 1 or 2, 3 base cases to figure out, as a verification, that it checks out. Here's another problem that, for now, I want to post it as a problem, and then at some point in the future, we have to solve it. It's related to that. In fact, we're going to use that to prove it. For the other section, I'm going to state it as a problem, and let's see who can solve it for me. And then maybe in a week or so, we all get at the solution. This is a very important sequence. Here's the problem. It's called the harmonic series. Hn is 1 plus 1 over 2 plus 1 over 3 plus 1 over n. And what we want to get there, so the main theorem is that this is approximately logarithm, this is a natural logarithm, ln of n plus a constant. Ln is the logarithm base e of n. where E, anybody knows who E is? Not the value, the definition. What is E? The base of the natural logarithm, yes.
But it gets the limit as n approaches infinity.
Limit of n goes to infinity of what?
Of 1 plus 1 over n.
It's true that's about 2.70 something, but this limit is fundamental in mathematics. In fact, calculus is not possible without this limit. The basic of calculus was put when Euler figured out this limit. So to get here, in the regular section we're done, because they just take, here's harmonic series, is that done, let's move on. We're not gonna move on, we're gonna try to understand why that is true. So we can't do that today, but here's what we can do. I'm gonna state the problems we need. So we need two lemmas. Well, actually one lemma. We need the fact that 1 plus 1 over n to the n is smaller than 1. So this means that the sequence 1 plus 1 to the n is actually monotonically increasing. You can see what I just wrote here. When you move from one term to the next term, you increase the value. So this series that you compute the limit for is actually monotonically going up, but not to infinity. It's going up to E. Now, this is not a simple problem to solve, but we can solve it. We also need the fact that the other sequence that I need here is 1 over n plus 1 at n plus 2. So this is the same sequence at which the exponent is 1 over this denominator here. This is so if I look at the sequence, this 1 over 1 plus 1 over n, but not at power n, instead of power n plus 1. See? This sequence here, let's not worry about in between them yet. It's almost the same as this sequence. It's 1 plus 1 over n, but instead of raising at power n, it's raised at power n plus 1. So whatever this guy was 1 plus 1/4 at the power 4, this guy is going to be 1 plus 1/4 at the power 5. It's not the same sequence. It's a different sequence because for every denominator, it has the numerator plus 1. What this is saying, this is monotonically decreasing. You can see what I'm saying. I'm saying as soon as you increase n, you make n to n plus 1 becomes n plus 2, you get a smaller value. So this sequence, which is very close to that sequence, this is monotonically increasing, and this is monotonically decreasing as a sequence. Yet, you can easily tell all these guys are bigger than these guys. Because look at this. This is 1 plus n plus 1. That's a power base. This is the exponent. And this is the same power base, but a higher exponent, right? So between this and that, it's a trivial thing to say this guy will always be smaller than this guy. So what happens? I have a set of increasing values here, a set of decreasing values here, yet those guys are always bigger than those guys. And we can prove that the gap between them shrinks to 0, right? As soon as you go into infinity, those two values become very, very close to each other. That means there's only one value in between. That value is E. So that's what we need to prove. To get to this statement here, we're going to need this inequality. This is easy. This is not easy. And this is hard. There's a difference between not easy and hard, right? So everybody can get this. It's obvious from the statement, just a bigger power. We're going to be able to get this in class, and I'm not sure about that. You can try binomial formula and you get two monsters and see what happens in there. We can try to prove it by induction, but it's not that easy. Now, if we have this inequality, the next step is to prove a consequence, which is very easy, from this inequality, is to say 1 over n plus 1, it's always smaller than the natural logarithm of 1 plus 1 over n. It's always smaller than 1 to the n. That's extremely easy to obtain by taking the natural logarithms on these terms. If you take the natural logarithm, you get from one inequality that's bigger than 1 over n plus 1, and from the other inequality that's smaller than 1 over n. So again, this is easy. This part requires some hard proofs, but once you get this done, make no mistake, this is discrete mathematics. This is not calculus. There's nothing with limits here. I mean, I told you it's a limit, but this inequality, it has to do with simply natural numbers, right? And this inequality is the same. Once you prove this, you should be able to get that. That's very fast. And how about from here to here? How do I show that this is effectively the logarithm once I have this inequality? If I sum up this for n1 equal 1, 2, 3, 4, you got to play a little bit of logarithms to get to here. So from here to here, it's an easy step. We're going to do that. The hard part in here is to prove this. So if you want to impress me, by Friday, can at least show me this proof. Why is this sequence always increasing? This one will require more effort. Now, some of these proofs can be done easier with calculus because we assume very strong, very powerful theorems in calculus that we didn't prove yet. So it's not easier with cheating. We use a powerful theorem from calculus and say, hey, using that theorem, I can get this done. Yeah, because that theorem is not that easy to swallow, right? You know the theorem that says something with the area. The function between this and this, the area has to be smaller than the whole rectangle if I have a function. Yeah, I mean, it sounds easy, but it's not that easy to prove. That theorem with the area is the integral, and it's smaller than the whole rectangle. We'll prove this. So we'll do that Friday. But we can't prove this theorem because we don't know enough calculus. Now the last thing I want to do in category of proofs by not calculating sums is to do a last proof which states a tree with n vertices, let's say v vertices, because it's vertices, has exactly v minus 1 edges. It's a proof that we already done, but we didn't do it with induction. So how do we prove by induction? I'm writing in English. Of course, later we have to formalize it in math. How do I say this with induction? I say if a tree has v vertices, it implies it has v minus 1 edges. That means any tree. That's the premise. It says, that's what I know. I know the property being true. This is my statement of size v, right? This is a property for size v. If it's true for v, it means any tree with v vertices has exactly v minus 1 edges. How would this look for v plus 1? The same statement.
For any tree with v plus 1 vertices, it has v edges.
Remember, when you do an induction proof, you gotta state the induction step first. You can't just say, proof by induction, da 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 da. These are my calculations. You need to state what the induction step is. This is the induction step. Now, like before, what's the core idea in induction step? To relate the new guy with the old guy. What's my new guy? That's my new guy. I want to relate this new thing with the old thing. So what do I have here? My new item is a tree with V vertices that I have to prove something about. How do I say this is somehow related to a tree with V vertices? I have to make that relation going on in order to make this proof work informally. Before I write something formal, I have to say, okay, that's the stuff I need to prove something about. I have to relate that new object with the old object for which I knew stuff about. So I need a way to relate those two. Somebody else, please. Yes?
You can take the entire tree except one vertex and say that that is the tree with V vertices and V minus edges.
So if I could say, hey, this new tree is actually, I'm going to put equal sign or 3 bars. It's actually the old tree. I think you mean something like, here's the old tree, right? Plus, this is the old tree, but it has this additional edge, right? It's not exactly that one. I drew a different one. So from here, I've got 3 branches. Let's do the same 3 again. These 2, this one. From here, I get 1, 2, 3, 4. And from here, I got this. Right? I think what he's saying is, look at this tree, the old tree, except this edge. And he's saying, if you imagine this edge as being separate for a moment, this is the old tree plus 1 leaf with 1 edge. Is that what you mean? That the new tree is actually some old tree plus 1 leaf that comes out. If this is true, and I'm not saying it is, am I done? Can I apply the hypothesis, the induction hypothesis for the old tree? Why? Because the old tree must have how many vertices? V vertices, and it's a tree. Therefore, I know from my hypothesis it has V minus 1 edges. This is the induction hypothesis or premise. So now if I know this, what happens when I add 1 edge to it? The number of edges here is the old number of edges plus 1 edge, right? How much is the old number of edges? V minus 1 plus 1, that equals V. However, this is not complete. This fact that he says, you take one tree, remove a vertex, like that's what you said, and then I get an old tree with V vertices. Is that statement true? Take a tree, remove a vertex, you get back a tree with V minus 1 vertices. Is that true all the time? If I just say like that, it's wrong, right? I can take a tree, remove a vertex, this vertex, and then I destroy the whole thing. Right? So this relating the new guy with the old guy, I agree the proof is very easy. If you could say, I've got an old tree with V minus 1 vertices, but how can I guarantee that that happens? Can I guarantee that happens? What vertex do I need to remove? One with degree 1. How do I know there is one with degree 1? So, is it guaranteed to have vertex of degree 1? Not mathematically guaranteed. I mean, we believe, as in wishful thinking, that needs to be proven.
We can say that every tree constructed into a grid tree.
That needs to be proven, that there is a vertex of degree 1. Yeah, we did. So, but you have to use that. You can't just say remove a vertex and you got an old tree, because that's not true.
The first thing we can reorganize every tree into a grid tree. Yeah. First order.
Did you eat breakfast?
Yeah. Yeah.
Yeah, for me it's like, it's really funny. It's like, what? No, yeah, I'll like forget to eat. And then I'll
It definitely is, but I don't need it.
Instead of 5, I know what it means. You have 2 hours. There'll be a lot of simple questions that take 5 minutes, and maybe 2 or 3 questions that requires about 15 to 20 minutes. So you can think of the DiscreteMath, 2 or 3 questions that will probably take an hour. Probably we're going to indicate those are the more simple. And a lot of small questions that will take a while. But we'll do some calculations, something with graphs, something with induction. So the simple one, I think, is like the quiz. And the more thinking one will be thinking, but not like in homework. Because the homework is too long.